So my presentation called Buildings as Batteries, I think it's, why are we calling it that? I think the question of what a battery is and how we define it, and what role batteries play and how we can harness that is what I'm focusing this presentation on. I'll just start quickly in terms of Buildings Alive, which is a commercial, it works with owners, operators of commercial buildings, institutional buildings, and so forth. We focus what we're doing on three kind of fundamental questions. Trying to help, using data science, help understand what the optimization potential of a building or a portfolio of buildings is. Having identified what that target might be, identifying actions to address that target through efficiency and demand management strategies. And then thirdly, measuring and verifying what actions we're taking and whether they are effective or not. So as I say, building on what Stephen has just said, the approach here for a effective demand side behind the meter storage kind of approach, it starts obviously with the building and tapping into the data that's used typically just to generate bills. So the most reliable, incontrovertible source of energy data would typically be going to generate electricity bills, but tapping into that through smart meters, tapping into weather data, which can point to opportunity, point to what the loads might be on a building and what work a building has to do. Other information such as occupancy data and other things that can point to load. Feed that into machine learning, modelling technology that can then form a judgment and provide daily, weekly, monthly feedback or forewarning to the building operator on what might be, how the building might be performing. Provide the facility to drill in further to see that in more interactive ways. And then, as Stephen was saying, for the owner of the building to be able to evaluate on a semi-regular basis how the building's performing. The level beneath that, which can be where the problems begin, I suppose, in terms of the technology access and so forth, is the sub-metering level. From that, though, if you can access sub-meters at the building level, you can find a lot more deeper insights and feed that into the same learning and modelling. Building management systems or building management information systems, building management control systems, Internet of Things, that data can also be used to generate virtual meters or fine-grained insights that can further explain how buildings performing and what the opportunities are. What I want to focus on here is this final piece of the puzzle, and what we're calling here grid interval carbon intensity data. So what we're talking about here is the time varying carbon intensity of the electricity system, which reflects the increasingly variable generation mix, and feeding that into the models to provide feedback to tune and optimize the building. So why is this important? Well, as no doubt everyone's heard over the last couple of days, the global electricity system really needs to shift rapidly to one that's dominated by dispatchable sources of energy to non-dispatchable sources of energy, such as wind and solar, which are clearly cheaper and more abundant in many places. As that happens over the coming decades, well, the role of different components in a much more complicated energy system just becomes clearer. So also released last week, quite an important document that you might want to have a look at. The Australian Energy Market Operator released its Integrated System Plan update to 2050. And what I found very interesting in this is not just the rapid growth of generation capacity that's projected from wind and solar, but the measures to try and maintain stability on the system, and particularly this purple wedge that you see here. So as we're moving away from coal and gas, this grid called Coordinated Distribution Energy Resource Storage becomes, roughly speaking, about 50% of the dispatchable capacity on a system in a few decades' time, from virtually nothing now. Why is this really important? Well, as you can see, these are different regions that Buildings Alive works in, and you can see here, if you look at a place like Poland, where there's variable wind component, or but it's fairly high carbon intensity measured on the vertical axis here, compared to, say, a place like California, where it's relatively clean but very predictable because of the nature of the contribution of solar. Or a place like South Australia, that should say South Australia, where it's a combination of wind and solar, representing more than close to 70% of the supply mix currently. Or Ireland, where it's primarily wind as the renewable energy source. What becomes really interesting when we start seeing growth in these non-dispatchable sources is the relationship with between the price of energy on the wholesale market, so what the generators receive, and the carbon intensity of that electricity supply. And as you see on the horizontal axis here, if you move to the left, cleaner electricity, and I should highlight each one of these dots represents the combination of carbon intensity and price at a half-hourly interval. Whenever it's cleaner, it's also cheaper, and in fact, quite often negative cost. This is due to the fact that demand on most systems currently is very unresponsive to wholesale price. Building operators are not seeing the wholesale price and therefore not responsive to it. So if you've got an oversupply of electricity from an abundance of wind and solar on the network, the wholesale market price drops. Without a commensurate change in demand, the price goes negative, which represents an interesting opportunity for buildings, not just from the point of view of providing support for the grid and the system operators, but for the building owner operators themselves. This was really brought into stark relief last year when the South Australian electricity grid, or the component of the Australian market, actually averaged negative price on the market, moving from where it was at $40 a megawatt hour in 2020 to averaging zero or below zero between 9:30 in the morning and 3:30 in the afternoon every day. That was largely maintained throughout last year, and it even exhibits this when we're in the midst of a global energy crisis. Not quite as low, but still. So what that would mean, if a building owner was able to access electricity through directly from the wholesale market, cost of their energy dropping from $40 or so to virtually nothing for the typical operating hours of an office building or an institutional building. So clearly a huge opportunity for building owners if they were to be able to tap into that. Also, from a reporting point of view, there's an interesting situation emerging. Here again, I'm showing South Australia's electricity system, which I hasten to say is connected to the national system, but it's got its own characteristics. You can see here last week the real-time, so the 15-minute interval varying carbon intensity of that electricity supplied in that system versus what you get if you use official reporting figures that you would use under the UNFCCC reporting obligations that every country has. So a static emissions factor multiplied by a certain amount of energy use is just simply not a true reflection of what the greenhouse gas emission impact of a unit of electricity actually is. If you shift to here, this is the New South Wales, so Sydney and the state New South Wales electricity grid. It's also quite interesting. Clearly a lot dirtier in the sense that a lot higher carbon emissions, but the real-time emissions are well below that static emissions factor. And what that's illustrating is another problem with static official emission factors is happening in the grid. Because solar electricity still receives a high price, there's significant growth in investment, and it means the official statistics are lagging behind. So what does this mean in application? What could you do if you're operating a building, or what might you want to do if you were trying to incentivize a different type of operation of buildings or a way of thinking about that? Well, here on this plot, I'm showing the blue line. This is the energy, and so the power consumption in kilowatts at hourly intervals for a building on the grid in South Australia, which I was just illustrating before. The red line is the carbon intensity of the electricity grid in South Australia. Now, what typically a building owner or operator would be doing would be trying to save energy during the middle of the day because that's when they use the most. But if we apply these two different factors, so what we call the National Greenhouse Accounting Factor, so the static factor, obviously the carbon intensity of the building's operation just reflects its energy profile. But if we use the real-time emission factor, we see that during the middle of the day, the emissions are actually not that high. And so instead of having an issue so much in the middle of the day, you've got two peaks, one at the beginning and one at the end of the day, which would be much more worth focusing on in terms of environmental impacts, but also because that's the way the wholesale price works, also from a financial point of view. This is, I know I'm focusing mostly on Australia and particularly South Australia, but just to illustrate from a building in California, the same sort of story exists there, where there's been a significant growth in renewable energy investment, in solar. You see the dotted red line being the carbon intensity of the electricity supply. The building's consumption is reflected by the blue line, and the reality in terms of its true emissions is reflected by the green line. And so they're quite right to be shifting as much of their load as they possibly can to the middle of the day and achieving an actual emissions reduction of 16%, or put the other way, using official reporting factors, they would be overstating their emissions by 16%. An example here of a building in a university, on a university campus, where they weren't so much interested in reducing the real-time carbon emissions, but rather shifting load to reduce capacity charges at the end of the day. So in this particular university campus, they pay a network capacity charge that's set based on the maximum demand from 2 p.m, so 1400 hours, to 8 p.m, 2000 hours. So what they did is, I should just point out a couple of other aspects of this graph. The columns here are the carbon intensity, which you'll be picking up now. The machine learning model predicted under this summer's day, the demand profile would follow something like the green line here. But what they did is they raised a temperature set point on the building by 1 degree Celsius at the beginning of the day and maintained that through to 2 p.m. So effectively forcing the plant to work a little bit harder up until 2 p.m. So they achieved what they were hoping for in terms of a demand reduction measured during that window of 2 till 8 p.m. But interestingly, they also achieved a greenhouse gas emission reduction 16% by shifting, well, effectively were able to run the plant equipment more efficiently, shift load to some cleaner energy, and reduce the overall amount as well. If we were to take that same action and apply it into a building that has a grid that looks more like the future grid that the IEA is talking about, so one that looks like South Australia's, which is overwhelmingly wind and solar, on a day where weather conditions were almost the same. So I've taken this building from one city and put it down in another city's grid. And the effect of that is really quite astounding. When they had a windy morning, but not a windy evening, and obviously sunny during the day, the effect of that would have been a 68% reduction in greenhouse gas emissions. So really quite phenomenal. So just to wrap up here, just with another dimension for why, you know, if we thought of buildings as batteries and thought about charging and discharging the thermal energy in the building, or enhancing indoor air quality, for example, this is a large shopping centre with a very large photovoltaic array on the roof, almost 1 megawatt of capacity. And I think it highlights another really important consideration for electricity networks and planning, the fact that the infrastructure itself can be optimised greatly if we take a more dynamic and active efficiency approach. The blue line here is what the building actually consumed in terms of electricity and what its demand profile looked like. The green is what the grid saw, because those solar panels are sitting behind the meter. Clearly, there's almost as much demand on the network, so the size of the cables, supply infrastructure had to be designed to accommodate that. But if some of that load can be moved from later in the day and shifted to earlier day, not only would the emissions be reduced, but the system capacity, so the transmission distribution infrastructure capacity, could be reduced as well, and more optimised. So with that, I will wrap up, and thank you.